Welcome to Ask and Learn.
Hi there. We're going to look at the question concerning the number of vertices that a full five-area tree with 100 internal vertices has. Now, that's actually a pretty straightforward formula to solve this, but let's derive that formula, and we're going to do that by starting with just the simplest form of the problem we can. Instead of worrying about a full five-area tree, let's just worry about a really simple binary tree. And that could look something like this, where we just have one parent vertex with two children coming off of it. Now that's a full binary tree since each vertex is either terminating or it has two children. These two on the bottom are terminating and the one on the top is the parent. And it also only has one internal vertex because an internal vertex is defined as anything that has children or other vertices directionally coming off of it. Now, since this is written with the direction with the direction of flow going down, then this top vertex is the only one that has things coming off of it, and thus it's the only internal vertex. Um, Hence, we're looking at uh, whoops, simple tree with just one internal vertex, but then it obviously has three total vertices. So the question we're trying to answer is how do we get from this number to this number? Well, if you think about it, if there's one internal vertex in a binary tree, that means there's one vertex that has children. And since it's a full binary tree, then it should have two children coming off of it. So this one top vertex leads to two, and hey, there you go. One parent plus two children equals the three vertices that we want. So that's a pretty simple solution. Doesn't really tell us exactly what the formula is still. But let's look at something slightly more complicated. Let's take a similar binary tree, but then add an extra layer to it. Now, this is still a full binary tree. Each parent has two children. But now we're looking at three levels. It has a height of three. Uh, so in this case, there are now three internal vertices because there's three vertexes here that have uh, children coming off of them. And when you look at it, there's seven total vertices. So now we're looking at 3 and 7. Now let's keep the same logic we had for the last tree and say, okay, if there's three total parent vertices, that means each parent vertice has two children coming off of them. Three internal vertices times two, that equals six total vertices. So this means we know there's six children. Now, what of these seven vertices, which six are those counting? Well, it's actually counting, and I'll mark this in green. I'll mark these six in green here. It's actually counting all the children. So if you could define any of these as children, then they're being counted in the six. So that's this one, and these four down here. It's not counting this top one because the top one here is a parent, and it has no vertices above it that are leading to it. Hence, we're able to count all six, but then we need to add one here to get back to our seven total vertices. So the formula becomes a little more apparent because you see that if we know that there are m branches off of every parent, so I'll put this in a new tab. If there's an m number of branches, so in this case it was a binary tree, so that was two. Then you can multiply that by the number of internal vertices that are. That's the number of total parents, if you're thinking it in that terms. And then we'll just label that as capital I for internal. M times I gives you the total number of children, but that leaves off that top one because no matter what M or I is, the tree will always look something like this, where it's going to have a bunch of stuff below it, but there's be one parent at the top that's not counted in the number of children. Remember, this is the number of children. So since that one's not counted in this mi, we just add one to that. And that gives us our total number of vertices. So going back to the original problem, m was equal to 5, I was equal to 100, and thus the formula gives us that vertices equals 5 times 100 plus 1, which equals 501. There's your answer.